Assalamu alaikum. Today we want to talk about chapter 14, some compounds with oxygen, sulfur or a halogen. 14.1 Alcohols, phenols and ethers. Alcohol is a compound that has an OH group bonded to a saturated alkane-like carbon atom. You remember in chapter 12 we said it is a functional group. Phenol is a compound that has an OH group bonded directly to an aromatic ring, benzene-like ring, also a functional group. Ether is a compound that has an oxygen atom bonded to two organic groups. You see here oxygen in the middle, bonded to two carbons or two alkyl groups. This is an example. This is an example of an alcohol, ethyl alcohol. This is an example of phenol. It is a compound phenol and it is a functional group. And this is an example of an ether. Notice here the oxygen is in the middle or is between two carbons. And you can call this diethyl ether or simply ether. Now, the structural similarity between alcohols and water also leads to similarities in physical properties. Look here, the molecular weight for ethyl alcohol, for dimethyl ether, and for propane, almost they are very close to each other. The boiling point of alcohol is 78, for ether minus 23, and for propane minus 42. And then if we compare all of these to water, molecular weight 18, boiling point is 100. Now the high boiling point of water is due to hydrogen bonding. Hydrogen bonds also form between alcohol or phenol molecules. Alkanes and ethers cannot form hydrogen bonds, and that's why they have the lowest or lower melting points. Some common alcohols. Methyl alcohol, or the IUPAC name is methanol, is known as wood alcohol because it was prepared by heating wood in the absence of air. Today it is made by reaction of carbon monoxide with hydrogen. Now, ethyl alcohol or ethanol, the IUPAC name, is sometimes known as grain alcohol and is the alcohol present in alcoholic beverages. Isopropyl alcohol has this structure. Glycerol is a triol also called glycerin, and it is the building block of triglycerides or triacyl glycerols. Now, naming alcohols. Step 1, name the parent compound. Find the longest chain that has the hydroxyl substituents attached and name the chain by replacing the E ending of the corresponding alkane with OL. Then, number the carbon atoms in the main chain. Begin at the end nearer the hydroxyl group, ignoring the location of other substituents. In a cyclic alcohol, begin with the carbon that bears the OH group and proceed in a direction that gives the other substituents the lowest possible numbers, as we will see. Step 3, write the name, replacing the number that locates the hydroxyl group immediately before the compound name. Number all other substituents and list them alphabetically. In a cyclic alcohol, do not use the number 1 to specify the location of the OH group. These are some examples. Here, we want to name this alcohol. We choose the parent alkane, 6 carbon hexane, and here we have two substituents. OH is the functional group, so it must take the lowest number. So we begin from this side, 1, 2, 3, 4, 5, 6. Then we put 5 hyphen methyl hyphen 3 hyphen hexanol. The parent alkane is hexane and we replace the E with ol, and the 3 indicates the position of the OH group. Now in this alcohol, the parent alkane is 4 carbon, 1, 2, 3, 4, and OH is on carbon number 1, so it is 1-butanol. 1-butanol. Now, if you have other substituents like chlor, for example, again OH has the priority to begin from this side and to give the other substituents their numbers. But in numbering, between chlor and methyl, we arrange them alphabetically. 4-chloro, 6-methyl, 2-heptanol. Again, this is number 4. We have chlor. We have 4-chloro, letter C before letter M. That's why we give it a priority. 4-chloro, then at position 6 we have 6-methyl, and at position 2 we have the parent alkane is heptane. We replace E with OL. Now in a cyclic alcohol like this, without CH3, this is called cyclohexanol. So if we have substituent, we give this carbon number 1 bearing the OH, and then we name 2-methyl cyclohexanol. Dialcohols or diols contain 2 hydroxyl groups in the same molecule. The IUPAC names of these alcohols are formed by attaching the ending diol to the alkane name. For example, here we have at position 1, 2, 3, we have at carbon 1 and carbon 3 2 alcohols. So we say 1, 3, the parent is butane, then we put diol. Here we have this substituents 2-methyl, then 1, 2 propan diol. Propan diol, or it's called isobutylene glycol. This is 1,2-ethanediol or ethylene glycol. This is 1,2-propanediol or propylene glycol. And this one is 1, 2, 3, 4, 5, 6, 5-methyl 2,4-hexanediol. Now the names will contain 2 numbers indicating the carbons bonded to the 2 OH groups, with the numbering starting at the end closest to the one of the OH groups, as we saw here. So we begin numbering from here. 1, 2, 3, 4, 5, 6. Diols with 2 OH groups on adjacent carbons are often referred to by the common name glycols. This is preferably reserved for 2 compounds, ethylene glycol and propylene glycol. Alcohols are classified as primary, secondary, or tertiary according to the number of carbon substituents bonded to the hydroxyl-bearing carbon. Remember, we classified carbons. You remember I said if the carbon is bonded to one carbon like this, it is a primary. If the carbon is bonded to 2 carbons, secondary. If the carbon is bonded to 3 carbons, tertiary. So accordingly, when the OH is bonded to a primary carbon, it is a primary alcohol. If it is bonded to a secondary carbon, it is secondary alcohol. And if it is attached or bonded to a tertiary carbon, then it is a tertiary alcohol. Properties of alcohols. Alcohols are polar because of the electronegative oxygen atom. Hydrogen bonding occurs and has a strong influence on alcohol properties. Straight chain alcohols with up to 12 carbons are liquid. Methanol and ethanol are miscible with water and can dissolve small amounts of ionic compounds. Both are also miscible with many organic solvents. That's why they are used as solvents in many chemical reactions. All alcohols are composed of a water-loving or hydrophilic part and a water-fearing or hydrophobic part. Here you see, if we take for example this methanol, this is the structure. This part in red is the hydrophilic part, the oxygen, and the rest here is the hydrophobic part. Hydrophobic, water-fearing or water-hating, and is therefore water-like. One heptanol, for example, again we have here the hydrophilic part, water loving, and all the rest are hydrophobic part or water fearing, and is therefore alkane-like. This is alkane-like, this is water-like. Alcohols with a larger hydrophobic part are more like alkanes and less like water. Reactions of alcohols. The first reaction called dehydration, removal of water from an alcohol. Alcohols undergo loss of water on treatment with a strong acid like H2SO4. Here OH from this carbon is removed with this hydrogen, with one of the hydrogens here to form water, and the result is this alkene, 2-methylpropene. We start with tertiary butyl alcohol. Notice here this carbon is tertiary, so it is called tertiary butyl alcohol. Dehydration, whether you remove OH and hydrogen from this carbon, or hydrogen from this carbon, or hydrogen from this carbon, you will get the same product because all of them are similar. So the reaction is driven to completion by heating. The OH group is lost from one carbon and an H is lost from an adjacent carbon to yield an alkene. As you can see, this adjacent carbon could be this, this, or this in this example. When more than one alkene can result, a mixture of product is formed. Now the major product has the greater number of alkyl groups directly attached to the double bond carbons. Notice here we have this OH. Now we can remove with OH one hydrogen from here. This is one choice, and then we get this product or this alkene called 1-butene in 20% yield. And if we remove OH with hydrogen from this carbon, then we will get this 2-butene in 80% yield. So why this is major and this is minor? Because the major product, as written here, has the greater number. Here we have two alkyl groups on double bond carbons. Here we have only one alkyl group on the double bond. From this side we do not have anything. So always the major product is the one with the larger number of alkyl groups. Now, reactions of alcohols, again, the favorability of this reaction is a function of the stability of the carbocation. For example, tertiary alcohols undergo this process more readily than secondary alcohol, and primary alcohols undergo the process very slowly. So we can say an ease of dehydration of alcohols is in the order tertiary alcohol more than secondary alcohol more than primary alcohol. Water acting as a Lewis base can remove an adjacent hydrogen, forming the alkene. Heating selectively drives off the alkene due to its lower boiling point. We have a rule called Zaitsev rule. It states that the more substituted alkene will be favored. Yani, if we go back here, why this alkene is favored? Because it has larger number of alkyl groups, and this is Zaitsev rule. It says the more substituted alkene will be favored according to this Zaitsev rule. Now the second reaction, called oxidation, occurs when primary and secondary alcohols are converted into carbonyl-containing compounds by an oxidizing agent. A carbonyl group is a carbon attached to an oxygen by a double bond. Any oxidizing agent can be used. In organic chemistry, a more general definition of oxidation reduction is used. An organic oxidation is one that increases the number of CO bonds and or decreases the number of CH bonds. An organic reduction is one that decreases the number of CO bonds and increases the number of CH. Now, two hydrogen atoms are removed during the reaction, one from the OH group and one from the carbon attached to the OH group. So here, if you have an alcohol and it undergoes oxidation, these two hydrogens are removed to form this carbonyl compound. Now primary alcohols are converted into aldehydes under controlled conditions, or carboxylic acid if an excess of oxidant is used. So here, oxidation of primary alcohol does not stop here at the aldehyde level. It goes all the way to form carboxylic acid as long as the oxidizing agent is present or we have excess of it. Secondary alcohols are converted into ketones on treatment with the oxidizing agent. You see here, when we remove these two, we form a ketone. However, tertiary alcohols do not normally react with oxidizing agents because they do not have a hydrogen on the carbon atom to which the OH group is bonded. So here, your tertiary alcohol oxidation put no reaction. So primary alcohol is oxidized all the way to carboxylic acid, secondary all the way to a ketone, tertiary no reaction. The word phenol is the name both of a specific compound, the hydroxyl benzene, as well as a family of compounds. Here, these are two examples. The parent compound here is phenol, and this chlor is in ortho position, so it is orthochlorophenol, whereas CH3 here in a para position, so it is paramethylphenol. So now, phenols. The properties of phenols are influenced by the electronegative oxygen and hydrogen bonding. Most phenols are somewhat water soluble and have higher melting and boiling points than similar alkyl benzenes. They are less soluble in water than alcohols. Alcohols and phenols are very weak acidic. They dissociate slightly in solution and establish equilibria between neutral and anionic forms. Here we have an alcohol. In water, it ionizes a little to this alkoxide ion, ethoxide ion, plus hydronium ion, whereas the phenol in the same way, it gives us this phenoxide ion plus hydronium ion. Methanol and ethanol dissociate so little in water that their aqueous solutions are neutral. However, an alkoxide ion or anion of an alcohol is as strong as a base as a hydroxide ion. An alkoxide ion is produced by reaction of an alkali metal with an alcohol. So, if you react sodium with water, we form sodium hydroxide plus hydrogen gas. However, if you react sodium metal with methanol, we form this sodium methoxide plus hydrogen. And this methoxide ion is as strong as a hydroxide ion. Phenols are about 10,000 times more acidic than water. A phenoxide ion is produced by a reaction of a phenol with dilute aqueous sodium hydroxide. So phenol plus NaOH dilute, we form this sodium phenoxide plus water. Sodium phenoxide plus water. Ethers are named by identifying the two organic groups and adding the word ether. Now, as I told you, oxygen is attached to two carbons. In this example, dimethyl ether. This example, ethyl methyl ether. You see separation here, and we put ethyl before methyl. Why? Because it's alphabetical. Ethyl methyl ether. And here we have diethyl ether. Cyclic ethers are often referred to by their common names. Ethylene oxide, tetrahydrofuran solvent, and 1,4-dioxane is also a solvent. These are solvents for organic reactions. Now, the OR group is called alkoxy group. CH3O minus methoxy, CH3CH2O minus ethoxy group. Now, ethers do not form hydrogen bonds to one another at all. Alcohols first, then ethers, then alkanes. Now, the oxygen atom in ethers can hydrogen bond with water, causing dimethyl ether to be water soluble and diethyl ether to be partially miscible with water. Then this oxygen can form hydrogen bond with water. So this one is miscible with water and this one is partially miscible with water. Ethers are alkane-like in many properties and do not react with acids or bases. Simple ethers are highly flammable. On standing in air, many ethers form explosive peroxides. Now, compounds that contain an oxygen-oxygen bond. Ethers must be handled with care and stored in the absence of oxygen. Now, thiols and disulfides. Many oxygen-containing compounds have sulfur analogues. Thiols, also called mercaptans, are sulfur analogues of alcohol. The systematic name of a thiol is formed by adding thiol to the parent hydrocarbon name. Ethane, thiol. Here, you number from this side 1, 2, 3, 4, 3-methyl, 1-butane thiol. Here, you number from this side 1, 2, 2-butene hyphen 1 hyphen thiol. This is to indicate the position of the thiol. Now, thiols react with oxidizing agent to yield disulfides. Two thiols join in this reaction. The hydrogen from each is lost. This hydrogen is lost, and a bond is formed between the sulfurs. So this two thiol molecules becomes a disulfide. The reverse occurs when a disulfide is treated with a reducing agent. So from left to right oxidation, from right to left reduction. This is called disulfide bond. And now halogen-containing compounds. The simplest halogen-containing compounds are alkyl halides, RX. Their common names consist of the name of the alkyl group followed by the halogen name with an IDE ending. For example, here you give it number 1, 1, 2, 3, 1 chloropropane. If you have two substituents, the halide is given we number from its side to give it the smallest number 1, 2, 3, 4, 5, 6. But in naming we put alphabetical order. يعني brom has a higher priority in numbering and also in naming. So 2 bromo hyphen 5 hyphen methyl hexane, 2 bromo. So the halogen atom is a substituent on the parent alkane. The parent alkane is named in the usual way. The halo substituent name is then given as a prefix, just as if it were an alkyl group. And here, since you have three similar atoms, we have trichloromethane, or the common name chloroform. This is the end of this lecture.